In this video I want to show you an important method which can be used to evaluate the derivative of a function numerically. For simplicity, we will start from a function written like that, so it's an analytic expression. And you can take the derivative analytically, so this expression here. Then what we are going to do is we are going to use two different methods to evaluate the derivative of this function numerically. The first method is a simple one, which is called the finite difference method. It works like this. You have to take the difference of the function evaluated at two adjacent points, and then you divide by the length of the interval, which is defined by those 2 points. Then we can use another method, and this other method is called the spectral derivative. This method consists in calculating the Fourier transform of the derivative and then using the inverse Fourier transform to evaluate the derivative. It is particularly useful because the Fourier transform of the derivative is quite simple to evaluate, because it is equal to the imaginary unit times the angular frequency times the transform of the function itself. And it is particularly convenient because you can always calculate the Fourier transform numerically by using the well-known FFT algorithm or fast Fourier transform algorithm. And then you can go back to the initial domain by using the IFFT or the inverse fast Fourier transform. I want to show you the results by using MATLAB. So let's move on to MATLAB. This is a MATLAB script that I have created. I will not get into the details of the entire script, but this script will allow me to do exactly what I described earlier. So first I define the function and also the derivative of the function. So this is the analytic derivative. df is equal to this expression on the right. And then first I do the finite differences method here. So I simply calculate the difference between the function evaluated at the point k and the function evaluated at the point k plus 1. And then we divide by the interval dx. And then I also do something similar for the spectral derivative. So I calculate the FFT of the function. I have the Fourier transform. And then I calculate the derivative of the function in the spectral domain by using the formula I, the imaginary unit, multiplied by the frequency, and then this is multiplied by the function lowercase f. And then we can go back to the initial domain by taking the inverse fast Fourier transform. So in here I plot the three different derivatives, the analytic one, the one calculated by means of the finite difference method, and then I have the one calculated by means of the Fourier transform. And then I also evaluate the error here. So let's run this script. Here I have the plot which shows me the derivative of the function evaluated in three different ways. The one in black is the function evaluated by means of the analytic expression. So it's the exact expression if you want. And you can see that the one in red, which is the FFT derivative, is very close to the analytic expression, whereas the finite difference method is this one in blue and it does not exactly overlap with the other function. So if I go and check the error here, you can see that as the number of samples increases, the error will decrease in general. But the error related to the finite difference method in blue is still greater than the error that I have in red here, which is related to the FFT method. In general, the spectral method is better, but we still have to be careful because there might be some phenomena, like for example the Gibbs phenomena, which is related to the oscillations of the Fourier transform. These oscillations might be related to the discontinuities that we have in the derivative, for example. We still have to pay attention. As you can see, different methods can lead to different results.